Hello everyone, I am Naka Johnson from the University of Liverpool and this is the module called 633. Today I am excited to share understanding derivatives, the foundation of change in mathematics. Over the next few minutes, we'll explore the origins, the formalism, the intuition and the powerful applications of derivative across science, engineering and AI. Our journey will follow this roadmap. Introduction: why do we need derivatives? Formal definition of derivatives. Derivatives, geometric and physical meaning. Common rules of differentiation. Example, differentiating a polynomial. Application and summary. In the late 1600s, two giants, Isaac Newton and Gottfried Leibniz, independently developed what we now call calculus. Newton convinced of changing quantities as fluxions, viewing velocity as the fluxion of position. Leibniz crafted the notation dy by dx, a concise symbolic system that elegantly captures instantaneous change. Their parallel work and friendly rivalry revolutionized mathematics and physics, laying the groundwork for modern AI. Why do we need derivatives? Why care about derivatives? Because they measure the rate of change, a concept central to understanding dynamic systems. In automotive engineering, our car's speedometer shows us the position with respect to time. In finance, marginal cost and rate of return are derivatives of cost and price functions. In AI and ML, training algorithms rely on gradients, that is, partial derivatives of a loss function, to iteratively improve model parameters. Derivatives let us understand, predict, and control systems in a real time. Formal definition of a derivative. Formally, the derivative of a function at a point x is defined as f dash x limit h tends to 0 f x plus h minus f of x upon h. This limit of secant slopes gives the tangent slope at a point. As h approaches 0, the secant line becomes the tangent, capturing us the instantaneous change. Now derivatives, geometric and physical meaning. Geometrically, the derivative of a point is the steepness of the curve y is equal to f of x. That point, as we can see in the graph, where there are two slopes, one is a tangent and the another one is the secant. As we can see, there are two lines moving, and as a positive derivative means the function is increasing, a negative derivative means the function is decreasing. Physically, velocity v of t is equal to s dash t. The derivative of position was the time. So velocity is the derivative of position with respect to time. Similarly, acceleration is the second derivative, that is d2 to s upon dt square. This is the double derivative, as we call the derivative of position with respect to time. These graphs show how slope changes interpret speed and acceleration. There are some common rules of differentiation. Here we have four rules: chain rule, product rule, constant rule, power rule, and these rules are used together to handle complex functions. Let us look at an example of how we will differentiate a polynomial. Given f of x is equal to 3x power 4 minus 5x plus 7. Now here we'll apply the power rule to each term. Differentiating the first term with respect to x, 3x power 4 gives us 12x cubed, and when we differentiate the second term minus 5x, it gives us minus 5. As we apply the constant rule to the third term, we'll get 0. So now we get the first derivative of the polynomial f of x as 12x cubed minus 5. Now we can calculate the position at x is equal to 2 by putting the value 2 in the place of x. So f dash 2 is equal to 12, 2 cubed minus 5, that is equal to 96 minus 5 is equal to 91. The tangent line at the coordinates 2, f2 is equal to 2, 27, which gives us the equation of line. That is y minus 27 is equal to 91 x minus 2. Moving on to the applications. Derivatives power critical application. Like in AI/ML, gradient descent updates weight via loss derivatives. Backpropagation. Repeated application of chain rule in neural networks are used using derivatives. In physics, computing velocity acceleration from position data. In finance, calculating marginal cost rate of return. Without derivatives, modern optimization and predictive modeling would be impossible. Now summarizing everything that we have learned, that derivatives quantify change in mathematical terms. They are foundation in AI physics and data science and finance. Mastery of rules and definition enables modeling and optimization of complex system, algorithms, and model behavior. Change is the only constant, and derivatives are how we measure it. Thank you.